So when we're looking at planar rigid body motion, it's important to note that these all kind of mean different things. So first of all, planar, we're talking about stuff that's moving in 2D. Rigid means it doesn't change shape. And body is different because usually by the time you get to this in dynamics, you've been looking at point particles. So what this means is not a point particle. Now, motion seems like it's probably like self-explanatory, but there's actually 3 types of motion that we are going to concern ourselves with. There's translation, and translation is basically something like if you have something that's this shape and it moves over here and it kind of keeps the same shape in the orientation. And then there's rotation, and that's something more along the lines of if something is here, then it's going to kind of move on one point. Now, it doesn't necessarily have to rotate from a point that is attached to it, so you could kind of imagine a little point down here that it rotates to. So this would be considered still rotation because it's rotating about a point, not necessarily a point on the part. And then, of course, you could have a comma. And in that case, yeah, I mean, it could definitely go from here, and then it can go to here. So it's not rotating about, I guess, no. We could make it move like this way, and then it's going to move this way, and then it's going to rotate. So there's no way that you could get to that without both rotating and translating. So planar rigid body motion, that's actually kind of a really, really important title that talks about all the different kinds of things you can do. Now, when I'm looking at this, I think about, this is really stupid, but y'all are just going to have to deal. Basically, whenever you're looking at this in dynamics, there's going to be a whole bunch of little topics, and you're going to start with a, here, I'll just kind of write it out. So there's a couple of ways that you can look at these. So we've basically got the idea that we can, if we're just translating, you kind of end up with this thing where, okay, we're going to try this one more time, and this time I'm going to record the rest of this video with the audio on instead of off. Okay, so we have these kind of 5 major sections that we're going to end up with in most of these books that are looking at it. Now, for the purposes of just kind of making it easier to look, so I'm going to call this, so we're going to do 1, 2. Now, even though we separate these in most books because mathematically it's complicated, kind of intellectually it's not that complicated to understand in that it's just like kind of a combination of the other 2. But whenever you actually get down into the math, it does get more complicated, so we separate them out. And then kind of here's the Cannonball version, which I'll explain. Okay, so let's look at translate only. So we've got this, kind of what I think about as like a dock. All right, so you can also call it a coordinate axis, but it's much more fun if it's a dock. And here is me, and I'm a girl, and I have a flower, and I'm happy. Okay, so I'm hanging out the dock as people who hang out at docks do, and I'm looking at this boat. And because I'm fascinated by boats, this boat has a cannon, which makes it even cooler, and I'm kind of obsessed with this cannon, and so I like to watch, like, I'm so excited about this cannon that I don't just watch the cannon, I watch the parts of the cannon, and I'm going to watch the base of the cannon and the tip of the cannon, because cannons are amazing. Okay, so as this boat is moving away from me, not only am I getting sad, and I'm watching this get further away, but I noticed something that's not terribly shocking, which is that as the boat moves away, the points A and B are moving at the same speed, as long as the cannon's not moving. So this is just pure translation, and as I'm watching the pure translation, I'm seeing that the velocity of B, I'm not being funny. All right, the velocity of B is going to be the exact same thing as the velocity of A, and the acceleration of B is going to be the exact same thing as the acceleration of A, because they're moving at the same speed, and it's super wonderful, and yay. Okay, so translate only, that's exactly what it does. Okay, now if we look at rotate only, remember I'm kind of obsessed with this cannon, so that's where this comes in. So here's me hanging out in the dock. I've gotten taller, apparently, with no torso. Let's try and fix that. I would like a torso, thank you. And my spine goes up into my skull. Is that how it happens? And here's my hat with my extra something. Okay, so I'm hanging out and I'm watching this boat, but now the boat is just going to kind of stick around because it's like, oh my gosh, somebody's watching me, so he wants to stick around and be impressive. So the boat is actually going to be anchored. What's an anchor look like? kind of like that. I don't know. Not a, got little hooks on it. I don't know. There's an anchor. So there's an anchor, and here's the base of the cannon, and here's the tip of the cannon, and now the cannon is just kind of like flexing like its awesomeness at rotating. Okay, so it starts there, and then, so this is also kind of annoying whenever you're looking at books, is they all have kind of different ways of showing where the motion is going. Some of them start with like dots where it was, and then solid to where it is. Some of them dots where it is, solid, or yeah, whatever, the opposite of what I just said. But the idea is that it's rotating. Okay. And now the idea is that the further away B is, however long the cannon is going to indicate how fast B is moving, basically. So the velocity of B is, and this is not a video on how to derive all this. This is just a video on how to kind of get some context as to where we're going. Kind of like that. Okay. And then the acceleration of B is actually going to have two components, right? You have the tangential and you have the normal. So in addition to kind of knowing how fast it's rotating with its angular velocity, I'd also know its angular acceleration, or alpha. So the tangential is going to be the component that's going this way. So that's just going to be the same thing, or very, very similar as velocity, is it's going to be the alpha AB crossing with RB with respect to A. Okay, so there's that, but there's also the normal component, right? And that's omega squared R. If you remember from kind of doing this in point particles, it's omega squared R. Now the thing is, in this, omega squared R becomes omega cross R. Okay, and again, this is not going into the details of how this is derived. This is just to give you kind of the two components. So you have the normal, sorry, this is the tangential, and you have the normal. Okay, and so it's really not that bad, I guess, is where I'm going with this. So then we have translation and rotation together. Okay, so this would be like me hanging out on the dock, and I'm going to try to have a reasonably sized torso. Here's my now apparently dead flower up on there. And now the boat is getting a little creeped out by me because I've just been staring at this boat all day. And so I've got point A and I've got point B. And so now this boat's trying to get away from me because I need to stop doing math and find something else to do with my time. Okay, so now as a threat, the cannon is now turning its attention back to me. I don't know why we've decided that the cannon's going to shoot through itself to try to get me. Maybe it's not. Maybe it's just trying to impress me. All right, so we have these two components. We have the translation and we have the rotation. And believe it or not, this is actually as straightforward as adding the other two components previous sets together. So basically, the velocity of B, it's going to move and it's going to rotate. So we're just going to add those together. Okay, so when you see these equations, they look kind of super intimidating, but whenever you kind of understand where they come from, they're a lot less so. So the velocity of B, first of all, it has to move, and then it has to rotate. Okay, and this is really stupid, and don't do this or don't tell anyone I told you this. Sometimes like the A with respect to B and B with respect to A are obviously different. And so the way I keep them straight is I think, oh, look, they cancel out, even though they really don't cancel out. So they don't cancel out at all. But if you put in, if you actually put in A with respect to B here, you're going to get totally the wrong answer. So I just stupidly think, oh, look, the A's cancel out, and I'm left with a B, which is what I have here. Yay. Okay, so don't really do that or in front of anybody, but you can do it secretly, like I do. Okay, so the velocity is just a combination of the two, and it's going to be the same thing with the acceleration. Basically, the acceleration is going to move, and it's going to have normal and tangential components of rotation, okay? But the problem is this just starts to look kind of ugly. So we have the acceleration of B is going to be the acceleration of A plus the tangential, that's the word I'm looking for, tangential. The tangential component, which is going to be the alpha AB cross RB with respect to A, so that's the tangential. and then the normal component, which is omega cross r b with respect to a. Okay, and these are all like that. Okay, so that's kind of like the kind of the combo. And as you can kind of see, this is a little bit intimidating looking. So usually in most textbooks, it's kind of broken up into its own chapter. Not chapter, but section. So these two are often separated just to kind of give you a little bit more time to practice. Okay, so then there's the one that I call just the Cannonball, translation and rotation plus Cannonball. All right, so this is the point where I've pretty much creeped out the boat. I don't know why all of a sudden this has gotten to be a dark story, but you know, here I'm like, this is me. I'm so sad because the boat is leaving. Okay, so that's all right. I'll find another boat one day, but that's okay. For the moment, I have this boat. So this boat used to be here, and the cannon used to be facing this way. But now, not only has it moved, the boat has moved, and the boat has turned around, or the cannon has turned, and they're sufficiently considering the option of moving this cannonball in my direction. Okay, so now we're actually going to look at the cannonball itself. So I guess the difference between what we have going on here is before we were talking about, so this is a little bit weird. Before we were talking about B being the end of the cannon, but that's not what we're doing anymore. Now what we're going to look at is B as being the cannonball. That's why it was B. That's not why it was B, but it helps. And so A is still the base, but instead of specifically just looking at the end of the cannon going back and forth, we're going to look at B as it's going. Now, before you freak out, this isn't a thing where we're actually going to try and figure out where the cannonball lands, because that is like way too much math. Really what we're just going to look at is this is going to be a snapshot. And all of these really are just snapshots, but it's never been more important than in this particular situation, because as you can imagine, every single second, and you could do this like in general terms of T, that's just not usually something that you're going to do dynamics. It's going to be at this moment, blah, blah, blah. If you're wondering where the whole cannonball comes through, it's really the concept of a slotted link. So usually you'll have a slotted link here that's rotating, and then you have something else over here that is rotating inside that slotted link, and you're looking at this. So you're kind of like following this, going back and forth. That's the cannonball, is this going back and forth inside the cannon. Honestly, also in most of these problems, the boat's not moving, because even if the boat isn't moving, it's still sufficiently complicated. So anyway, just to kind of let you know. But this helps me kind of understand the concept of something is moving and rotating and all that kind of stuff, because the equation looks pretty weird. Okay, because it does start out the same. Okay, so we do have that the velocity of B is given by the velocity of A. So first of all, the boat's moving, and at any specific time, if I'm looking at the snapshot, it's going to be omega cross r B with respect to A. So we're going to get that rotational motion. Okay, but then there's the one more component, which is basically how fast is the cannonball moving. And the only way to know that is to send a spy to hang out here and sit in a chair and like watch the cannonball go away. So actually, let me do it this way. So now I'm going to be even super creepier. And I'm going to put up a little spy camera. Like by spy camera, I mean apparently dude in a chair. So dude in a chair is going to be sitting, now he's going to be upside down. That's all right. So dude in a chair is hanging out here watching the cannonball. Okay, so then the last piece that we need to add is how fast is the cannonball moving? And what we do is we call that the velocity of B with respect to A as seen from an observer in the XYZ plane. Okay, so I'm going to say that again. It's the velocity of B with respect to A. So the velocity of the ball with respect to the starting point as seen from an observer who is rotating with the system. So you see how the dude rotates with the cannon, so he doesn't notice. So from his point of view, this is, so like this is around, and this is out. So this is the cannonball going out. So this is away, around, and out. So this would be kind of along the lines of the ball moves down the cannon at 3. So not a very impressive cannonball, I guess. But, you know, that's kind of the idea, is that if you're measuring the speed of the cannonball from the, you know, perspective of the cannon, all this is me sitting over here in this universe. What is the speed of the cannonball that I measure? Okay, so that's kind of where we're going with all of this. And again, most of the time you're going to see these in problems in the homework in like slotted links, or like planes are moving in weird directions and stuff like that. But it all depends on what context you're coming from and where you're looking at it from. Okay, now, funnily enough, by the time they get into this, they're doing all of the this is all going to, a lot of times, be in the same section. So you have the same thing going on with acceleration. So the acceleration of A is going to be given by, the acceleration of B is going to be given by the acceleration of A plus that rotational component, the tangent component, R B with respect to A. All right, plus the omega cross R B with respect to A. All right, but then you have a couple of more components, because you say, oh, well, then clearly I just need to add the acceleration of B with respect to A in the XYZ plane. And you'd be almost right, okay? You'd be almost right. You'd be so close, except not quite there. The one thing that you'd be missing is the Coriolis force, and that's just like a combination of, whatever you call it, a combination of how fast the cannonball is moving with respect to the boat, and basically it comes into here as 2 omega of AB cross the velocity of B with respect to A as seen from an observer in the XYZ plane. And again, I don't have a better way to explain this quickly than just to say, hey, it's the Coriolis. And then, yeah, you can absolutely add on the acceleration. Whoa, that looks weird. The acceleration of B with respect to A as seen from an observer in the XYZ plane. So you've got the away component, you've got the tangential, you've got the normal, and these are both kind of the around, the tangential and the normal of the around. Then you have the Coriolis, and then you have the out. So again, the ball is shot accelerating at, 5 miles per hour squared or whatever. So that's what you would measure if you were sitting on the cannonball watching it go. So that's kind of where these equations are coming from, and it's a little weird to think about it, but I think that it's kind of helpful just to realize that as you're looking at these and getting a little bit like overwhelmed, that they're just all components of the same thing. And the good news is that a lot of times things will end up being zero. Like most of the time these will end up being zero. The boat's not even moving because that's too much work. We're just going to watch the cannonball run around. So they're not nearly as bad as you think they could be, but hopefully this gives you at least some context to think about them.